We left off doing confidence intervals, and I just wanted to remind you of what that looked like when we did it on Friday. We have our usual structure of the formula of our statistic, plus or minus. We have our z-score for the critical value, and then this was our standard deviation formula. And we got that by adding the variances. And I had said that the major difference in this process is that we now have a new formula, and we also are going to have, when we check our conditions, remember that we need to check, since we have two separate samples, we need to check our conditions for each of those samples. So there's a little bit more that you'll need to write on the conditions. The formula looks slightly different, and aside from that, most things are going to be relatively the same. So today we're going to look at hypothesis tests. And let's start by talking about how we construct our null and alternative. Remember that our null hypothesis for things are usually that there is that there's no difference or no change, or usually a statement of equality between the two things. And then the alternative is what gives us the change and gives us the direction of that change. So when we're comparing two different proportions, usually what we're comparing is we're trying to detect whether there's any difference or whether there's any change, and if there is, what direction that change is in. So that means that our null hypothesis, if we're talking about our statement of no difference, is that means that the two proportions are the same, that they are equal. And so you can either state that your null hypothesis is that P1 is equal to P2, or that P1 minus P2 equals 0. Those are saying the same thing. If we subtract P2 from both sides with that equation on the right, then we get the equation over on the left. Right? If the two proportions were the same, then if I subtract two numbers that are the same, then I should get 0. And then our alternative will give the directions. Again, it's really important that you define which one is P1 and which one is P2, because that will tell you what direction the alternative is in. You can also, if it's going to help you, or if you prefer, you can also state it. The formulas will have to be in terms of P1 minus P2. But if it helps you in stating your null and alternative, you can state your null in this way, P1 equals P2. And then you can state, this one would be saying that P1 is greater than P2. This one would be stating that P1 is less than P2. And then this would be stating that P1 is not equal to P2. This would be my two-sided. And so if you're worried about doing the subtraction in the wrong direction, then you can state your null and alternative in this way. But then you'd still have to do P1 minus P2 in the formulas. And it's just a matter of preference of the way that you would write it. And again, conditions, random, normal, and independent. One more thing that's a little bit different. This is the main thing that's going to be new with these hypothesis tests. So remember that when we do our calculations and when we check our conditions, in our mean and standard deviation, we've been using P naught. In other words, we've been assuming, our calculations have been assuming that the null hypothesis is true. And the same thing when we check our conditions. When we do n times p for our normal condition, we do n times p naught, n times 1 minus p naught. That was something we talked about last chapter. So we're saying, what does it mean for the null hypothesis to be true here? Well, for the null hypothesis to be true, what that means is that P1 and P2 are the same. So we need a value to give for what this proportion would be. In other words, if we're saying that P1 and P2 are the same, that doesn't say what specific number it is. It just says they're the same. So the way we're going to do that is by what we call pooling the proportion. So if P1 equals P2 is true, the two parameters are the same. Their common value is going to be P, but we need a way to estimate P. So basically what we're going to do is take the data from the two samples and combine them together. Again, this is something your calculator is going to do for you, but I want you to understand what it's doing. So it's basically taking the two samples and saying, well, if the proportions are the same, then we can take this as one sample from the same population and say it's the combined count of successes, the combined number of times it happens, over the combined count of individuals in both samples. In other words, the number of times the thing happens in total across both samples out of the total number of individuals in both samples. So what that's going to look like is x1 plus x2 over n1 plus n2. So sample sizes go on the bottom. This is going to make more sense when we do it in the formula. So in our standard deviation formula, we're going to use this pooled proportion in our calculation for standard deviation. We're not going to use p hat 1. We're not going to use p hat 2. And same thing when we check the normal condition. We're going to use this pooled proportion, and it's going to be p hat sub c is what we're going to use and what the calculator is going to use. Again, this will you'll see this better once we actually do it in an example. But that is something that we'll need to do in step 2 and step 3. Again, random, normal, independent. Oh, my mistake. Back up. N times P. We are doing the same conditions for normal as we did with confidence intervals.
So we don't use that change one or the PC. We don't use that one in the normal.
Not for the normal. You're going to use it when you calculate, but in the normal, you're just going to do n times P1, n times 1 minus P1, and then n times P2, n times 1 minus P2, the same way you did in the
last
the last one. Yes.
Okay, that makes sense.
Yes. And then there's your total formula. Again, this part is 0 because that's what the null hypothesis says. This is our value, and then this is statistic minus parameter. So this is our value minus the mean, and then this is your standard deviation formula. And again, if the null hypothesis is greater, then we're looking at the right tail. If the null hypothesis is, or if the alternative is less, then we're using the left tail. If it's not equal to, then we're interested in both tails. That's a two-sided test. Let's go on to an example here. So I'll give you just a moment to read. And then we will take a look at it. So because it's asking, do the data give convincing evidence of a difference? It doesn't give a specific direction. We're going to have a two-sided test. So our null is going to be that P1 minus P2 is 0. Our alternative is that P1 minus P2 is not 0. And let me actually let me show step 2 real quick first, because our conditions are going to be the same here. So let's see. We have, again, this is called a two proportion Z test. We're using two comparing two proportions here, and then z-scores, and then it's going to be a hypothesis test instead of a confidence interval. So two proportion z-test, or the book calls it a two sample z-test for proportions, as long as you're specifying that we're talking about proportions. And I'm just going to flash these on the screen real quick because you should have these conditions down by now. Random, each sample is random. Says that they're both simple random samples. Normal, we can do n times p hat for each of these. There they are. They're all at least 10. And then independent, since more than 1,500 students attend each school, then we have our 10% condition satisfied. Remember, for your independence, be careful how you phrase it. Sometimes I've seen some people phrasing it not quite right. What you're checking is that you take your sample size, multiply it by 10. That's the 10% part. So make sure you don't say 10% after that, because you just did the 10% by multiplying your sample size by 10. So you're going to do 10 times your sample size and then say that that's smaller than my population. So we're taking 10 times the 150, which is 1,500, and we're saying that our population, the number of students at that school, is larger than that 1,500. That's what we're saying. Now, let me talk through, it's going to show it in step 3 here, but let me talk through the reasoning for getting our pooled proportion here. P hat sub C is saying, let's combine these and treat them as one sample. So instead of treating, because if these two proportions are the same, then they're coming from the same population. And so if that's the case, instead of thinking about it as two separate samples of one of 80 and one of 150, let's combine these together and say that our total sample size is 80 plus 150. And then if we're combining them as a total, here's the number of people that had not eaten breakfast. That's going to be 19 and 26. So what we're saying is that if these are all coming from the same sample in the same proportion, then we would be saying that out of 230, out of 230 total across both samples, there were 45 total across both samples that had not eaten breakfast. So that is our pooled proportion. Again, that is saying, if the null hypothesis is true, then that means that these two proportions are the same. So we could treat them as coming from the same sample. So that 45 out of 230 is what's going to go on the standard deviation formula in my fraction. So that's what we're going to do. So what we've done so far, just to recap, stated our null and alternative. We decided it was two-sided because difference. We defined our P1 and P2. It says our alpha level is 0.05. So that's our step 1. Step 2, we said what kind of test we were doing. It's a two proportion Z test. And then we checked our 3 conditions, random, normal, and independent. Step 3, we're going to do our calculations. So there's our pooled proportion. It's 0.1957. And that's going to go in our standard deviation formula. So again, it's a z-score. And we're going to need formula, plug in your numbers, answer.
Should we show the PC thing in this step, or is it unnecessary?
I would show it.
Okay.
I would show it in there. So we have that z-score and the probability for the z-score. We would take 2 times that probability. Since it's a two-sided test, we want both tails. And the p-value is 0.2420. That's greater than our alpha level. Failed to reject. Not enough evidence for the alternative. So again, the thing to notice here is that this pooled proportion, the 0.1957, it went into the standard deviation formula here, 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 and here. And then our p hat 1 and p hat 2 went on the top of the formula in our value. Minus our mean is 0 because we're treating these as being the same. So our z-score came out to be 1.17. And then this is what our p-value turned out to be. Our step 4 sentence is basically the same. So I will pause here and have you and give you about 30 more seconds to take a look at that and write that down, or get pictures if you need to. And then we will go on to talk about the calculator. Here comes calculator time. Stat, over to tests. And what we just did was a 2 proportion z test. And it's just going to ask you for your values. So if you've been familiar with it thus far, then this shouldn't be too bad. 19 out of 80 and 26 out of 150. Okay, so we have 19 out of 80 in sample 1. Remember, these need to be whole numbers. So if you come out with a decimal from n times p, then you need to round it. And then 26, right? 26 out of 150. And remember, our alternative was that we had a 2-sided test. So we had the P1 was not equal to P2. Calculate. There's your z-score. There's your p-value. And here is your pooled proportion. So this is my p hat sub c. And then, as always, this is your z-score. This is your p-value. So again, this idea of the pooled proportion is the biggest new idea that we're looking at today. Everything else should be more or less the same. The way you put it in the calculator is pretty much the same. The way you're going to write the rest of your steps and the process are pretty much the same. So we're going to look at one more example here. And I will let you read it, and I'll actually give you about maybe about a 5-minute or so head start on this one, so that we can zoom by it a little bit faster here. So take about 5 minutes or so and see what you can do. Oh, apparent benefit. That sounds like a direction to me. So this sounds like a 1-sided test this time. Give it a go. By the way that this study is set up and designed is fairly similar to how you might test something like efficacy of a vaccine. You would have a placebo group and you would have a group that takes the vaccine, and you would track whether the person would contract the disease. And you want to see if there's any statistically significant results in their exposure levels and whether they contract whatever virus you're hoping to get vaccinated for. And how much lower of an amount of people get the disease is how efficacy gets measured. So if there's supposed to be a benefit, then we are hoping for the people in the drug group to have a lower rate of heart attacks than the people in the placebo group. That would be the benefit, is fewer heart attacks. So the way we should frame our null and alternative is that if we have P1 be our drug group and P2 be the placebo group, then our hope is that P1 is less than P2. Or that P1 minus P2 is less than 0. And in this case, if you used a 0.05 alpha level, that's fine. They're saying that they want to use a 0.01 alpha level to reduce the risk of making a type 1 error. Because if you use a lower alpha level, then you're going to reject less often, which means you're rejecting incorrectly less often. In other words, we don't want to put a drug out on the market that doesn't work. And so we are erring on the side of caution in that regard. That means a type 2 error is more likely, but we are reducing our chances of a type 1 error. So that's what your null and alternative should look like. Here come your conditions. 2 groups in a randomized experiment. If you say SRS here, you're not going to get credit. We did not take a random sample. We put our participants into 2 separate random groups. That's the random part of this process. Here's our normal. Here's our independent. The book frames these in terms of like successes and failures. I usually put it in terms of the thing happens or it doesn't. And so the thing happening in this case would be a heart attack. So by the book's definition, a heart attack in this case would technically be a success because it's the thing we're tracking. Individual observations should be independent, or you can check your 10% condition. These counts are all at least 10. Normal condition is good to go. Here comes our 2 proportion z-test. That's what our pooled proportion should be. Negative 2.47 should be your z-score, which means the p-value is 0.0068. So we're going to reject our null hypothesis. There is enough evidence of the lower heart attack rate for people who took the drug than for people who took the placebo. So just to show you the calculator very quickly, and then I'll bring this back. Let's see, 56 out of 2051. All right. So stat over to tests. We're doing 2 proportion z-test. (2051). And then our second group had 84 out of 2030. And again, we're hoping for P1 to be less than P2. We're hoping that the drug is lowering the rate of heart attacks. Oh, wait, that's not right. I put something in wrong. Hold on. I I find, I fix. 56.
Yeah.
There it is.
Sorry.
Got it. There it is. So that is our calculator. Very quickly, remember that I have given the first homework assignment. You should be able to do everything on this homework assignment now. And then I will go back and leave this screen up so that you can finish writing the rest of this down.